Hello. So, in this video we are going to be proving that if f is a continuous function on the closed interval a to b, then in fact it is Riemann integrable on that. So, first I'm going to recall a result. Well, really the very first thing I'm going to do is let epsilon greater than 0 be given. And as if that wasn't a tip off, we're going to be doing an epsilon delta argument type thing here. So the first thing after that I'm going to do is I'm going to recall something. So this is from previous semester. So since f is continuous on a closed and bounded interval, f is in fact uniformly continuous. So, if you don't remember, that is to say, for any let's call it epsilon prime, just so I don't confuse it with epsilon, greater than 0, there is a delta prime greater than 0, such that for any x and y in my interval, so here AB, if that x and y is suitably close, meaning less than delta prime away, then I have that the image, the f of x and f of y, are close together, i.e. less than epsilon prime. Now, the thing I want to sort of point out with uniform, so this uniformly continuous business that's key, is that this delta that I'm choosing, this delta greater than 0, or delta prime I should say, does not depend on x or y. It is one delta to rule them all, as it were, right? It is a uniform choice. It works over all of the interval. And that's really important for a lot of reasons, as it turns out, but it'll be very important in this particular proof. So I want to recall this in case you don't remember. So in particular now, so this is sort of a off to the side here, the recalling what it actually means. So in particular, there is some delta greater than 0 such that for any x and y in AB, if, that's not that, there we go, x and y are within delta, then f of x minus f of y is less than. And now this will seem to come out of thin air, but it's going to come out of thin air because I have sort of already looked ahead and know what it needs to be. So if you're doing this on your own, sometimes what you can do here is leave this blank, continue on as if you had done it, and by the time you get to a point where you need it, and we'll see what I mean by that, you can come back and fill in the sort of a value you need. So we can discuss that more. That's a thing you should have covered a lot in the first semester, but if you're not sure about it, then obviously feel free to ask me during office hours, email, whatever. So back to this. In particular, I want this to be less than epsilon over b minus a. Okay? All right. So, and to be clear, this epsilon is now the one that was given, not the epsilon prime. Okay. All right. So far, so good. So now, I'm going to fix a partition P x0, x1, etc. up to xn, so that I have some features here, or a feature. So it's a standard partition, meaning the x0 is a, the xn is b, and it's an increasing sequence of numbers. I'm not going to go through all that again. But the other thing I want is that so there's a shorthand I'm going to start using that's very common, which is that I say for 1 less than or equal to I less than or equal to n. We obviously know what 1 is, we obviously know what n is, so what I'm really saying is for I, obviously going to be an integer by context, between 1 and n. Okay, so I'm sort of declaring for I such that I between 1 and n. This is common shorthand. I want that the distance between xi and xi minus 1 is less than delta. Okay, so I'm fixing any partition you feel like. It has some n number of these things, but importantly, the distance between any two of them in order, right, any consecutive two, is less than the delta that I defined up here, this delta. Okay? All right. So, also, I'm going to observe sort of one more thing before I get to the calculation bit, and then it all sort of magically works. So I'm also going to observe, since xi minus 1 to xi closed is closed and bounded, by the extreme value theorem, EVT, f attains its max and min. That is to say, i.e., that there is some, let's call it Ci and Ki, such that little, let's say, capital Mi is the Ci, and little mi is the Ki. Sorry, f of. That should be f of these things. I was like, this doesn't look right. There we go. So this should be f of Ci, and little mi is f of Ki. So all I'm saying is this is a closed and bounded interval, so my f hits the max and min somewhere. That's the extreme value theorem. And so I'm labeling a point, there might be more than one, but I'm labeling a point where it hits its max as the Ci, the point at which it hits its max in the ith rectangle, and the part where it hits the min, or a part where it hits a min, I'm going to label Ki for the ith rectangle. So if it hits more than once, just pick one. I don't care, right? This is there exists, right? There is one of these things somewhere. Okay? All right. So, last but not least, right? I want to show this thing is Riemann integrable. So as we've seen before, and as I mentioned when we did this thing, I'm just gonna, for clarity's sake, say I'm sort of branching off to another bit here. I want to show that U for this PF minus L for this PF, I want to show that this thing is less than epsilon, right? If I can do that, I'm all set. That by that other theorem tells us that it's Riemann integrable. So what is this? This is the sum, I going from 1 to n, of the xi minus xi minus 1 times mi minus the sum I going from 1 to n, xi, my marker's running out here, sorry, minus xi minus 1 times little mi Okay, but I know that I have these ci and ki, right? So this is going to be, I'm going to put these things together, because again, they're finite. So I'm going to have xi minus xi minus 1. That's common in both of them. So then I'm going to have the mi, which is really f of ci, minus the little mi, which is really f of ki. Okay? So that was putting the sums together and translating the capital M and lowercase m to their other pieces here. But note, so maybe off to the side here, I'll just say, note that by design, right, these ci, ki's, they're both in the same interval, meaning that the distance between ci and ki is less than the distance of the whole interval, which I chose to be less than delta, right? But if that's true, if I have the two x values less than delta, right, then I know that this piece is less than epsilon over b minus a. So this is less than I going from 1 to n, xi minus 1 of epsilon over b minus a, which now this thing doesn't depend on my iterating variable. So this is just equal to epsilon over b minus a times the sum I going from 1 to n of xi minus 1. And that is just sort of the most bare bones, quintessential telescoping series you can have, right? So since it's telescopes, it's going to have the biggest piece, xn, minus the smallest piece, which is x0. But xn is b, x0 is a. So this is actually equal to then, oops, sorry, getting ahead of myself here. Still have the epsilon out front, the epsilon over b minus a. So I'm going to have the xn, which is really b, minus the x0, which is a. But then b minus a cancels the b minus a, and that's epsilon. So I have my upper minus lower, and then I have equals equals less than. So upper minus lower less than epsilon. So then, f is Riemann integrable on a to b. There we go. So this is sort of what you would hope to be the case, because continuous functions are supposed to be pretty nice, right? So the hope is that this is about as nice as you can get it, and indeed that's what happens, right? So here I have any continuous function is indeed Riemann integrable without knowing anything else about it. All right. And we're done.